There's no question that large-scale climate engineering is untested and dangerous. We've mostly thought about sulfur, and there's a lot of good reasons to think about sulfur because sulfur is what nature does, and there are very good reasons to think we would like to start very slowly if we ever wanted to do this and do something that was an analog to nature because we have some idea what the downsides of what nature does are. Nevertheless, there might be some good reasons to think about alumina. It turns out, first of all, there's been a lot of work on the environmental consequences of alumina in the stratosphere because it's in shuttle exhausts. There's a bunch of papers that look at the radiative and ozone-destroying properties of alumina in the stratosphere, and those make you think it might be useful. The big deal really is that alumina has 4 times the volumetric radiative forcing for small particles as does sulfur, and that means you have 4 times less surface area for the same radiative forcing. And this is a much bigger deal. You'd have roughly 16 times less the coagulation rate, and that's the thing that really drives removal. So you could get away, we think, with much smaller mass fluxes. But we haven't run those studies yet, so that might be wrong. The little picture is from a nanofabrication study, which shows you can make very high quality, and do this in just a jet in a very simple way, make high quality alumina particles just by spraying alumina vapor out, which oxidizes. So it's certainly in principle possible to do that. There's a big literature that's already looked at that. Look at the alumina or sulfuric acid functions, which are the mass-specific backscatter, so a measure of radiative forcing, and in fact I have it in watts per square meter per megaton. And those things fall off as the particles get larger, but even more important, the fall speed rises quite rapidly in this regime. And so as particles stick together and get large, they fall out of the stratosphere very quickly. And so particles that are too large are much less effective per unit mass. Aerosol geoengineering looks like it is so cheap that the cost is basically not going to be an issue. That means that implementation decisions will be risk-to-risk decisions. The risk of doing it against the risk of not doing it. And it makes the problem of how we govern it fundamentally harder and different and novel. Another reason why I think more knowledge is good is I think this will turn out to be more complicated and harder to do than we now think. So I've told you that it's cheap to deliver materials to the stratosphere, and I'm convinced that's true. I don't think that will change. But I think the more we do research, the less easy this will look, the more complicated the environmental effects will look, and that's a good thing, because right now it looks too easy. So I think that if we do more research, we're likely to find out that it's harder and more complicated than we thought, and that the side effects are harder to manage, and that's a healthy outcome that will make it easier to do the management. It's an empirical question, how people will actually react to knowledge about this. Another reaction is to say, if these crazy scientists are so concerned about putting CO2 in the atmosphere, they want to think about these things, then that might actually mean we should be more serious about the risks of CO2 in the atmosphere. And by the way, it's not really a moral hazard, it's more like free riding on our grandkids.
Well, I mean, we don't even need our climate models to predict some of the basic changes you'd get from reducing the amount of solar radiation that's absorbed by the planet, which is what SRM geoengineering is aiming to do. By doing that, you're going to cool the planet. That's the aim. But you're also going to reduce sea level rise. Sea level tracks quite closely, or is connected closely with changes in the ocean temperature, and it's the changes in temperature that will melt the ice that will contribute to sea level too. So some of these basic things we know will change, but beyond that, we need to bring in our climate models. And these tell us so far that we can expect the intensity of the hydrological cycle to be reduced. So we're going to have less precipitation and less evaporation around the world. If we look at only at the short term, we can see trends in climate that may be misleading. This is the case, for example, with the global warming, the so-called global warming hiatus, where it seems that the planet hasn't warmed, but really you need to look at a longer time series to really see how the climate is changing. The same would be true for SRM geoengineering. After deployment, it'll take a long time to see how the climate is changing. So we'll have to rely on our models to help us to understand how the climate will change. But those changes won't be visible very quickly. We can use observations of those changes to help us constrain our model estimates to confirm whether or not certain changes of the climate are due to geoengineering or not.
In this short video, I'd like to give you an introduction to the topic of climate engineering. What is climate engineering? How and why has a controversial discussion around the topic arisen? And what is some of the jargon? How can we untangle that to understand climate engineering? Another big problem with solar radiation management techniques is that they would only be a band-aid solution. They would only address the global temperatures. They wouldn't reduce the amount of carbon dioxide in the oceans. They wouldn't help with the ocean acidification. Another major issue is that if we started down the road of using solar radiation management techniques to cool the planet and still let greenhouse gas emissions continue and greenhouse gas levels continue to rise, if it's someday in the future we had to stop for any reason, the temperatures would rise very, very rapidly back to what they would have been if we had never done the solar radiation management in the first place. And finally, because of the possibility that individual actors, unilaterally or in small coalitions, could implement solar radiation management to their own benefit without large concern about the welfare of the rest of the planet, the governance of this becomes very, very tricky. So, in addition to mitigation and adaptation, there are two basic streams of thought. One of these is removing carbon dioxide from the atmosphere, CDR, and the other one is reflecting back more sunlight, solar radiation management. Together, these are called climate engineering, or another term that's used for them a lot of times is geoengineering. Now, in addition to climate engineering and geoengineering, there's a whole bunch of different names that are in use for this, such as climate systems intervention, or novel options, or earth systems engineering and management, or planetary management, or planetary modification, or even planetary manipulation. And some are even proposing that because these techniques are so different from each other, that we shouldn't use any umbrella name. We should just simply talk about the individual techniques as they are. A real problem with these umbrella terms is that they're often used inappropriately. For instance, sometimes people say no climate engineering field experiments on a large scale have been conducted so far, when they mean no solar radiation management field experiments on a large scale have been conducted so far. A number of different names are also used to describe CDR and SRM. For CDR, in addition, carbon geoengineering, or greenhouse gas removal, or negative emissions technologies. And here we have the problem that often CDR is confused with CCS, which means carbon capture and sequestration. Other names for solar radiation management include radiation management, sunlight reflection methods, with the same abbreviation, SRM, solar geoengineering, targeted climate modification, albedo modification, or a reflectivity modification. Here again we have problems with misuse of terminology. In particular, SRM is very often misused to only refer to stratospheric aerosol injections, or SAI. Now, as you can imagine, there are a lot of serious and difficult questions to consider around climate engineering, such as what kind of techniques have been proposed in the first place? There are probably over 100 proposals out there already, and how well would each of these work? Well, that would take scientific studies of each of them to know. Another really difficult question is, are we allowed to control the climate? Are we allowed to influence our environments on this scale? And who even decides about allowed to or not allowed to?
Idea there was going to be a lithium dispersed until I heard payload lithium dispersed.
Right, there was lithium dispersed, and I'd be happy to talk to you about it. I think you might be under some misconceptions about what we're doing, but I'm happy to tell you any details that you need.
Well, I know that it says in your article that you're doing it for communications.
Okay, I'm happy to talk to you more about it. There are many reasons we're doing it.
Okay.
We don't understand how the wind in the upper atmosphere moves.
Mm-hmm.
In these chemtrails, there's different kinds of chemtrails, as you probably know. Different trails at night we use and different trails during the day. The wind blows them around. They glow either on their own or from scattered sunlight. We take pictures and we can see how the wind trail moves around and use that to infer what the wind is. Just like if you were taking a picture of an airplane contrail, you can use that to see how the wind was blowing up at those altitudes. This is much higher altitude, so we use these chemical trails.
And what is the purpose of knowing what the wind's going to do in the ionosphere?
The purpose is the ionosphere is really to understand our planet. It's very fundamental science. We're trying to understand every day. We know there's electric currents that flow over the head. They're just naturally there. They've been there for ever since the Earth had an atmosphere and a magnetic field. And the wind is driven by the sun. The sun heats the atmosphere. The wind blows. And every day that wind drives an electric current. And we're trying to understand what causes that. Essentially, how does it work in detail? And also importantly, when the sun becomes active with lots of sunspots and lots of magnetic activity, that changes the wind pattern and changes the electric current. So we want to understand both what it is on a regular day when there's no solar activity, and then what it is when there's a lot of solar activity.
Is there some other kind of a way that you can use it without dispersing the lithium?
We're researching other ways. The lithium is actually harmless to the environment, and we could show you more about that, but it is tricky to use because it's very faint. You can't see it with your naked eye. You have to, have special cameras to see it and so on. So we don't like to use it for that reason. It's hard. In other words, it's hard measurement to make. We're researching other ways to put sensors directly on the rocket to measure the wind, and those are ongoing. We're trying to develop those now. In fact, one of the purposes of this mission was to do that.
Okay. Well, you've explained it to me then. I don't agree with it, but I appreciate you explaining it to me.
Email too if you have detailed questions, anything you want.
Okay, I will. I'm gonna research a little more, and I will email you. And I appreciate you taking the time out to speak to me today, sir.
Get your call. It's not often we get to hear from members of the public and people who are really interested and concerned with what we're doing. I really appreciate your time.
I wish more people would call. I really do. I've called my senators. I've called my governor. You can't get through to anyone, sir. You can't get through to anybody.
Yeah.
I go to my city council. I live in rural North Carolina. They don't care. They laugh you out of there. There's no other recourse for us, sir, unless to talk to people directly and find out what is going on, because we're paying for it.
Another example is the array of technologies, often referred to collectively as geoengineering, that potentially could help reverse the warming effects of global climate change. One that has gained my personal attention is stratospheric aerosol injection, or SAI, a method of seeding the stratosphere with particles that can help reflect the sun's heat in much the same way that volcanic eruptions do. An SAI program could limit global temperature increases, reducing some risks associated with higher temperatures and providing the world economy additional time to transition from fossil fuels. This process is also relatively inexpensive. The National Research Council estimates that a fully deployed SAI program would cost about $10 billion yearly. As promising as it may be, moving forward on SAI would also raise a number of challenges for our government and for the international community. On the technical side, greenhouse gas emission reductions would still have to accompany SAI to address other climate change effects, such as ocean acidification, because SAI alone would not remove greenhouse gases from the atmosphere. On the geopolitical side, the technology's potential to alter weather patterns and benefit certain regions of the world at the expense of other regions could trigger sharp opposition by some nations. Others might seize on SAI's benefits and back away from their commitment to carbon dioxide reductions. And as with other breakthrough technologies, global norms and standards are lacking to guide the deployment and implementation of SAI and other geoengineering initiatives. Now, I could go on and on and on and on about the things that fascinate me, but rather than talk about them, I thought I'd stop here and start the conversation with Judy, and then I can take some of your questions. I very much appreciate the invitation to come back here in the Council on Foreign Relations And as I say to all the groups I speak to, it is a tremendous honor and privilege every day to be referred to as the Director of Central Intelligence Agency. I lead an organization full of patriotic men and women who take great risks and put themselves on the front lines in order to keep their fellow Americans safe and secure, and to do what they can to keep this country's security secure. Thank you so much.
What the proposed technologies would actually come into being as and what they would do, which are crucial and which I think that we know awfully little about given the state of the modeling at this point. There are a whole other set of uncertainties around how these things could or couldn't be governed and how society would respond to them, how society would respond even to the prospect of them. And the really difficult thing about all of these categories is that it's unclear how much you can say about them in advance, and that's a real problem. So the technical way of putting that is that if you're talking about starting to deploy and doing a small-scale study, you're talking about starting to do a small-scale study of something. If it's small-scale, do you get any information out that would actually help you decide whether or not it was a legitimate technique or a good idea? Socially speaking, similarly, you could think that, well, we think we know how to talk about these in a way that will make it completely clear that we absolutely have to mitigate and have to adapt and have to do everything that we would do anyway. But it might be the case that if you develop even theoretical approaches to a certain point, that turns out not to be true from the social perspective, and it's very hard to anticipate that stuff. And the governability, even if you were confident that the physical techniques could do what some people think they will do, and I'm not confident of that myself. The question about governability, divided, complicated global society with class distinctions and national distinctions and different interests and incredibly complicated governance structures, respond to these technologies in a way that involves, that's fair and equitable and just and that respects humanitarian concerns and ecological concerns and so forth. It's very hard to tell, and I think that that's a deep problem. We have a group called the Geoengineering Scenarios Working Group, and we started off doing fairly traditional scenario exercises, and we think they've been interesting, but classical scenario planning has this problem. You get a bunch of people together, and they have a lot of time to think about something that they've heard a lot about, and there may be cases in which, even though the point of the technique is to let you explore these far-flung possibilities, people talk each other out of interesting outcomes. And participatory approaches can be structured in different ways. For example, you can set up a game, and you can say, the experience that we want you to have as a game player is one in which you're trying to win, and your ideas about how things should work or how things do work in the real world are suspended for the moment. There are also techniques that some of us are starting to experiment with in this field and in climate generally that involve faster turnarounds. So, for example, rather than giving people 2 days to mull over possibilities, you give them 30 seconds. You say, okay, well, what if this happens? And now, what if this happens? And if you do that enough, with enough people in enough different contexts, on enough different questions, maybe that'll let us explore some of the corners and interactions in a way that surprises everybody, which is important in a conversation that runs the risk of following a few standard paths that were laid down years ago and which aren't necessarily going to lead us to the most productive and vital questions for this really deadly serious topic.
Our climate is changing. Greenhouse gases emitted by humans are warming the Earth. This has serious implications. Oceans are acidifying, sea levels are rising, deserts are expanding, and extreme weather events may become more common or more severe. We can prevent some of these consequences by reducing the emission of greenhouse gases.
This tackles the problem at its root. It's called mitigation.
However, we also have to anticipate some consequences. Since we've been emitting greenhouse gases for a very long time, some changes cannot be prevented by mitigation.
Therefore, we have to adapt to some changes. This is called adaptation.
Both require a lot of effort. Is there no easier way? If we humans are already changing the climate today, can't we just change it intentionally? Let's take control. Welcome to climate engineering. Let's manage the climate on a large scale and with surgical precision. Two methods can help us with that. Either we extract greenhouse gases from the air to slow down the warming of the atmosphere, or we reflect sunlight from the Earth, then temperatures will drop quickly. How does it work? Here's an example. We can capture greenhouse gases by building artificial trees. They remove CO2 from the air.
In principle, we already have technologies that could do that, although they would require a very large amount of energy.
And where can we put the CO2? It needs to be stored safely and for a very long time. And there will be a lot of it to store.
Or, well, we can also sink the CO2 in the sea by fertilizing the ocean. That makes algae grow, and just like trees, algae bind CO2. When algae die, they sink to the bottom of the ocean and simply take the CO2 with them.
Well, that's the theory. But how much CO2 could actually be taken up by ocean fertilization is really uncertain. What is certain is that there would be risks, especially because algae is a key link in the food chain.
Algae gets eaten by small animals that get eaten by larger animals, and so forth. Messing with the food chain can have fatal consequences.
Furthermore, ocean fertilization can cause the production of laughing gas, an extremely effective greenhouse gas.
Laughing gas? Laughing gas? Don't make me laugh!
We have another trick up our sleeves. It's getting too warm. Then let's dim the sun. Sunglasses for the Earth have an immediate effect. Cool! We can, for example, inject sulfur particles into the upper atmosphere to reflect sunlight.
That sounds simple. Less sunlight would mean less global warming. We know that the rising concentrations of greenhouse gases will have serious consequences. But could we actually balance increased greenhouse gases simply by reflecting sunlight? Well, we might be able to stabilize the global temperature on average. But reflecting sunlight does not have the same effects as reducing greenhouse gases. No one can tell exactly what the consequences would be. In some regions, we might have much less rainfall, or sometimes a lot more.
Well, that's great.
It's not certain that this will have negative consequences. Why shouldn't we just try? And if the experiment has bad consequences, well, then we can just stop it.
But if we have to stop the experiment, the Earth would warm in a very short time. We wouldn't have solved the problem with the greenhouse gases simply by reflecting sunlight.
But who gets to decide whether we reduce our emissions or adapt or manipulate the climate? No one has asked me.
These options are not mutually exclusive. Climate engineering can buy us time and is a last resort in case of an emergency.
Ha! And is it you who decides what an emergency is?
Artificial trees, ocean fertilization, or a sunshade for the Earth. Even if technological interventions might solve some problems, they would also create new ones, and it is unclear who should decide about their use. In short, we should think about climate engineering very, very carefully. In the meantime, let's first focus on mitigation and adaptation to reduce the risks of climate change.